Let's get into First Principles Daily, Episode 13. Let's break something down to its raw materials and build the reasoning back up. Capturing carbon dioxide from air today costs hundreds or thousands of dollars per ton, yet thermodynamics sets an energy floor far below that price. Direct air capture plants now spend hundreds to thousands of dollars to pull 1 ton of carbon dioxide out of the atmosphere. That single ton must be gathered from a gas mixture so thin that the target molecule makes up only a tiny fraction of what passes through the system. The concentration is only about 400 parts per million, so every cubic meter of air holds just a few grams of the target molecule. To gather a full ton, therefore, requires processing on the order of 2.5 million cubic meters of air, and every one of those cubic meters must be moved across a surface that can capture the sparse molecules without letting most of them slip past. Physics nevertheless fixes a minimum energy cost for separating and concentrating that dilute gas. The gap between that floor and current delivered prices is large enough to matter, because the difference represents real engineering and institutional choices rather than an unbreakable limit set by atoms themselves. The question is where the excess cost actually lives, and whether any redesigned path can close a meaningful fraction of it. Most existing direct air capture systems rely on solid or liquid sorbents that bind carbon dioxide when air is passed across them. These sorbents sit inside large contactor structures whose job is simply to bring the dilute air into intimate contact with the binding material for long enough that a useful fraction of the carbon dioxide sticks. Then the systems release the gas when heat or vacuum is applied. That release step, called regeneration, must reverse the binding without destroying the sorbent so the material can be used again. The process repeats in cycles, and each cycle requires energy both to move enormous volumes of air and to regenerate the sorbent. Because the incoming concentration is low, the contactor structures must be large, which drives up the capital cost of fans, ducting, and support frames. Those fans alone can consume a sizable share of the total electricity, and the frames must be strong enough to hold the sorbent while withstanding wind loads and thermal expansion over years of daily cycling. Plants are still built one at a time, often on greenfield sites that require custom permitting, grid connections, and water treatment. Financing and construction delays add carrying costs that compound before any ton of carbon dioxide is captured. Supply chains for the sorbents themselves remain small, so unit prices stay high and replacement schedules are conservative. Heat is frequently supplied by natural gas or grid electricity whose price and carbon intensity vary by location. This prevents steady-state operation at the lowest possible marginal cost. Operators also face strict requirements on water use, waste disposal, and land footprint that further constrain design choices and raise engineering margins. The result is that reported costs per ton sit well above $100 and in many cases several times higher. Yet these figures feel normal inside the small industry because every project has carried the same set of constraints from the first demonstration onward. The thermodynamic minimum work required to separate carbon dioxide from air at roughly 400 parts per million and deliver it at 1 atmosphere is set by the entropy of mixing. A rough calculation based on the free energy of dilution yields an energy floor on the order of 20 to 30 kilojoules per mole of carbon dioxide. That number comes from the fact that the molecules are already thoroughly mixed with nitrogen and oxygen. Pulling them out requires reversing that mixing, and the free energy cost of doing so at such low concentration is fixed by physics. To turn kilojoules per mole into kilowatt hours per ton, first note that 1 ton of carbon dioxide contains roughly 23,000 moles. Multiplying 20 to 30 kilojoules per mole by 23,000 moles gives roughly 460 to 690 megajoules per ton. Dividing by 3.6 to convert megajoules into kilowatt hours produces a reversible work figure of roughly 130 to 190 kilowatt hours per ton. Adding realistic conversion losses and real-world inefficiencies, raises the practical floor to something like 150 to 250 kilowatt hours per ton once conversion losses and real-world inefficiencies are acknowledged. That figure is only the reversible work. Any real process must also overcome kinetic barriers, pressure drops, and heat losses. So the practical floor is higher, but still measured in hundreds of kilowatt hours rather than the thousands that current plants consume. If that minimum energy could be supplied by electricity at 5 cents per kilowatt hour, the energy component alone would sit well below $20 per ton. Adding the cost of the actual sorbent material, steel or concrete for the contactor, and basic balance of plant equipment produces a rough magic wand estimate, still under $50 per ton before any profit or financing. Current delivered costs are reported in the low hundreds to low thousands. This implies an idiot index of roughly 5 to 20 or more depending on the plant and the accounting boundary. To see why the number lands there, start with the magic wand floor near $50 per ton. Divide the actual plant cost by that floor. The result shows the finished system carries 5 to 20 times the raw material plus energy cost, and sometimes more. The excess does not sit in the raw atoms of the sorbent or the steel. It accumulates in the oversized air contactors needed because cycle times are long. It also accumulates in the custom fabrication of those contactors. It shows up in the permitting and financing overhead that stretches schedules. And it appears in the repeated heating and cooling of large thermal masses during regeneration. Each of those stages multiplies the effective cost per ton without changing the underlying physics of separation. A redesign effort would start by treating the thermodynamic minimum as an explicit design target rather than an academic curiosity. That means choosing sorbents whose binding energy is close to the reversible work so that regeneration heat can be supplied at lower temperature and with smaller temperature swings. It would next attack the air contactor itself. The effort would ask how much surface area and residence time are truly required once the sorbent kinetics and the target capture fraction are fixed. Then it would explore whether modular, factory-produced contactor units could replace site-built structures. Scaling manufacturing volume would have to be paired with policy stability that reduces permitting timelines and allows multi-year offtake agreements. Capital cost only falls when the same design is replicated many times. Cheap, steady, clean electricity remains essential. Without it, the energy component cannot approach the floor. The genuinely hard constraints are the dilute nature of the feed, which cannot be wished away, and the fact that avoiding emissions at the source is still cheaper than recapture in most cases. Even so, the gap between present costs and a physics-limited floor of a few tens of dollars per ton is large enough that sustained attention to sorbent chemistry, contactor geometry, and supply chain repetition could move the delivered price downward by a factor of several without violating thermodynamics, a process whose price greatly exceeds its thermodynamic minimum, is announcing an engineering and institutional problem, not an immutable law of nature. Questioning the requirement before optimizing the hardware that meets it often reveals the largest levers. The same logic that once collapsed the cost of steel or silicon can be turned on dilute gas separation if the floor is kept visible. Who will publish the first detailed energy balance model that treats the thermodynamic limit as a hard constraint rather than a footnote? And what will be the first measured drop in regeneration energy per cycle that follows from it? That's a wrap on today's First Principles Breakdown. The ideas travel further when you pass them on. Send this to a fellow builder. I'm Patrick in Vancouver. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network, links in the show notes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.
I'm about to prove